So loans and investments, which is topic 1, are generally very formula heavy. So I gave your brain so many different formulas to think about when we covered that. Graphs and networks is a little bit different. It's not so much formulas, it's more like definitions and understandings. So that works better for some people and that's trickier for some people. So whichever way that is, we're gonna get into it. So graphs and networks. To kind of simplify the confusion, graphs and networks, they're pretty much the same thing. I'll give you the slightly different definitions later, but they're pretty much just referring to the same thing. So this is an example of a graph or a network. So a network, graph, or diagram represents the connections between objects. So that's, in essence, the summary of what we're looking at. It represents the connections between objects. Here we can see that this line connects B and G, this line connects A and F, and it's comprised of edges and vertices. You can see the vertices are like the points, and the edges are the connections. So for example, this graph or network here, it could represent connections between friends, it could represent who knows who, it could represent trains connecting different towns. There's a number of different things they could represent. They could represent almost anything where there's connections between different things. So a graph refers to a structure formed with edges and vertices. So for example, this is vertex H, this is vertex A, this is an edge connecting those two vertices. So like I said, vertices are the points and the edges are the connections. And technically, a network refers to a graph in which the edges and vertices have some special meaning attached to them. So they're very similar definitions, so we use them interchangeably. So technically, if this did not have any meaning associated with it, technically it would be a graph. But if this represented connections between different towns, then it would be a network because it's got a special meaning associated with them. But again, we very much use them interchangeably, so they're very similar definitions. So to practice applying that knowledge, how many vertices does this graph have? And remember, vertices are the number of points. And if you've counted them, A through H, you would have seen that there is 8. Question, how many edges? We can see that there's also 8. And you can also note that they don't all have to be straight. This one is a curved one, for example. So edges don't have to be straight. And another thing I'd love you to notice is that B and G are connected by 2 different edges, and that's called having multiple edges, when there's multiple edges connecting the same vertices. And finally, we have an edge that starts and ends on the same vertex, and that's called a loop. And that's, for example, what we have on vertex C here. So, more terminology. What is the degree of vertex F? And hint, remember that the degree is the number of edges that meet or leave the vertex. And that would be 2. If you can see here, we have, what do we have, F? We can see that there are 2 edges connected to vertex F, so it's got a degree of 2. What about the degree of A? You can see it's got 4 edges connected to it. What about the degrees of D and H? Well, it's actually 0. They're isolated vertices because they have no connections to any of the other vertices. And another thing that's really interesting is that C actually has a degree of 3 because it's got this edge here, but it also has a loop. And a loop actually adds 2 to the degree of a vertex. So it can be helpful to think of the degree as the number of different ways you can leave a vertex. So it's important to note that a loop adds 2 to the degree of the vertex. What about these ones here? So this one on the right is actually an example of a subgraph of the original graph. So what is a subgraph? It's essentially any graph you get when you remove edges and or vertices from the original graph. So some information is removed, but no new information is added. So it's part of a larger graph, but again, there's no new information in a subgraph. And so you can see that E was removed and all of its connected edges, and the loop on C, and both isolated vertices. So we can see that that information was taken away, but nothing new has been added. A simple graph has no loops and no multiple edges, and note that this is actually also a subgraph of our original graph. We've just had some parts taken out to make sure that there is no loops and no multiple edges. So we've turned it into a simple graph. A complete graph is where every vertex is connected to every other one. You can see that here our 2 vertices are both connected. Here all 3 vertices are all connected to each other. All 4 are connected and all 5 are connected here. And another interesting thing to note is that all complete graphs have n, bracket n take 1, divided by 2 edges. So that can be a helpful formula if you ever need to apply that in a question. So another type, we can also have weighted graphs. So that's when an edge has a weight associated with it or a number linked to each edge. And that number could represent a different thing depending on the graph. It could represent the number of litres that could flow through a pipe. It could represent the number of cars, of traffic that could pass through a certain area. It could indicate the road length in kilometres. These weights have a meaning or an association in the network. So we have an example of that here. You can see that this edge here has a weight of 5. This has an edge of 3. We're not told here what it means, but we can see that it does have weights. We can also have a directed graph or a digraph where edges have a direction associated with them. And this can help us model and communicate the direction of something. That could be water flow, traffic flow, different things. And digraphs, so a graph with direction associated, can also be weighted. And edges in a directed graph are known as arcs, and the direction is shown by having an arrow on the arc. So here you can see that there is a one-way connection from G to B, but we also have a one-way connection from B to G. You can see we have a one-way connection from A to C, but you actually can't get back to A. It's only a one-way direction. So that's interesting.